So today, as David said, I'm going to be presenting some of the recent CVL features. This is really everything that's happened since CVL1. So this is features that have been introduced in CVL2 and new features that we've worked on even since then. And there's a lot of stuff to cover. So this is going to be a little bit of a whirlwind tour. I'm going to assume that that you are familiar with the prover. I'm not going to go into a lot of background about about how to use the prover in general. I'm just going to show you sort of what's new recently. So let's get started. Quick overview. A lot of the changes in CVL2 and since have been in the methods block and in the way that you write down summarization. So the first set of features I'm going to talk about are related to the methods block and how you write methods block entries for summarization, and then some new features that are actually in beta right now, which you can get if you install the beta client or will be available in our next full release, which give you more power for writing summaries. We also have some new features for accessing the state of the blockchain during the verification. So we now have a built-in way to access the ETH balances of contracts and to compare different contracts or compare contract storage at different points in time. CVL2 also brought a major overhaul to the way that integer types work. It's much more streamlined now and much easier to understand. So I'll go through those changes. And we also have a new feature called a satisfy statement, which allows you to produce examples of when things go right in addition to producing examples of when things go wrong. And then at the end, all of this stuff is documented, and on my last slide, I have links to all the different parts of the documentation. So you can take a look at those for more details about all of this. So let's go ahead and get started. As I said, I'm going to start by talking about the changes to the methods block. So in CVL1, methods block entries were, kind of terse. You needed to give the name of the method. You needed to give the argument types. You could give a summary. There are other things you could write. You could write a returns clause, although you didn't have to. You could write an env-free annotation, and that actually hasn't changed. But there's some information that's missing here. And in CVL2, we've required you to add a lot of that information. So in CVL2, entries are much more specific. So this is the same entry as that, but in CVL2 syntax, there's a couple of things that have changed. So the first thing is we've added the function keyword and the semicolon at the end. This is just sort of generally, since we were changing the syntax for CVL2, we wanted to make it a little more consistent and a little more rhyme better with solidity. And so we added the function keyword, and there are semicolons required in a bunch of places you might expect them, and this is one of them. So minor syntactic changes, but there are bigger changes here. So the next thing to point out is here, I've mentioned a specific contract. In CVL2, every methods block entry refers to a single implementation of a method in a single contract, unless you explicitly ask otherwise. And I'll show how to do that in a slide or two. If you leave out, you can still leave out this contract qualifier here. But if you do, instead of meaning any allowance method in any contract, like it did in CVL1, in CVL2, it defaults to current contract, the contract that you're actually verifying. This allows you to have more fine-grained control over what you're summarizing. So one of the difficulties that we had with CVL1 was you couldn't summarize, if you had a transfer method and you wanted to summarize it in one contract and not summarize it in a different contract, you were kind of out of luck. In CVL2, it's very clear what gets summarized all the time, and it's whichever contract you name or current contract. So that's an important change. Another important change in CVL2 is you'll notice there's an external here, and in CVL2, every entry has to either be internal or external. And there's a couple of reasons for that. One is similar to focusing on a specific contract. You may have both internal and external methods that have the same name and argument types, and you may want to summarize one of them and not summarize the other one. This also is related to some of the changes that I'll talk about in a few slides, allowing better control over or more ability to interact with methods that take reference types, for example. Those are internally handled differently for internal and external methods, and having this annotation here makes the prover more able to do the right thing and more able to access more types. So every methods block entry has to be either marked internal or external. I'll talk in a future slide about what to do with public and private methods as well. The other change here, in CVL1, the returns clause is optional. In CVL2, it's mandatory. So if you don't write a returns clause, that means that you're expecting the function to not return anything, and you'll get an error if it actually does return something. So that just gives you a little bit more checking to make sure you got the methods right. Okay. So as I mentioned, you have to write either internal or external, but in Solidity, you can write internal, external, or public or private. Why don't we have public and private in CVL2? Well, there's a couple of reasons for that. But the main reason is that in Solidity, you can write private or public, but when Solidity compiles the contract, those concepts are erased. They're not present in the bytecode. And the Sartora prover is operating on the bytecode. And so it doesn't really have a notion of public or private, only internal and external methods. So to know how to summarize or how to write methods entries for private and public methods, you have to know a little bit about what the Solidity compiler is doing. Okay. So as I said, it's going to get rid of private and public. It translates those away. How does it do that? Well, if you write a private method in Solidity, that gets treated the same as an internal method. And so if you wanted to summarize a private method, you would just write an internal entry in your methods block. So that's pretty easy. The way that public works in Solidity, a public method generates both an internal and an external method. So the Solidity compiler will spit out both an internal and an external implementation. If I have this function G, I now have two functions G. And the internal one does whatever you wrote in your Solidity source code. The external one just calls the internal one. So when you go to write a summary, if you want to summarize a public method, you have to decide whether you want to summarize the internal one, the external one, or if you want, you could summarize both. Usually what you want to do is summarize the internal one, because then internal calls to this method will use your summary, and external calls will call the internal method, which will use your summary. So usually just summarizing the internal method is good, but in some situations you may want to, for example, only summarize the external calls, but let the internal calls use their original implementations. And this gives you the flexibility to make that decision. So that's how private and public are handled. They get translated internal and external, and you write the summary that covers the case that you care about. The other thing I want to mention is, as I said before, in CVL1, if you wrote a methods block entry, it just applied to every method that had that name and those arguments. And while CVL2 doesn't work that way, that's still a useful feature to have. So in CVL2, you can still get that behavior, but you have to ask for it explicitly. And the way you do that is with what we call a wildcard entry. So here I've written a methods block entry for a function called name, but instead of explicitly saying which contract I'm talking about, instead I put this underscore, which, like in other places in CVL, means pick any contract you like. And so in this case, this will match any contract, any name method in any contract. And then we'll summarize it, in this case, with a non-det summary. So these wildcard entries let you get that behavior of, I just want to, get rid of all my name methods, for example. Now, one important thing to notice here is that there's now not a returns clause. And the reason for that is when I'm looking at the same method in multiple contracts, it might return different types. And so we can't, I mean, there's no sensible way to check, whether these many different methods all have the given return type. And so we just decided you can't write a returns clause for a wildcard entry. Okay. The other thing to note about wildcard entries is they are explicitly for doing summarization. So some of the other methods block features, like writing env-free annotations, are disallowed, and you have to write a summary if you have a wildcard entry. Because otherwise, for the other uses of methods block entries, wildcards don't really make sense. So this lets you get all of the methods of all of the methods with a certain signature in any contract. Also, occasionally you'll want to just summarize all the methods of a contract without regard, I don't care about this uninteresting library and its behavior, so I just want to summarize it all away for in order to get my verification to go faster. And so there's a shorthand for doing that, which is you can use the wildcard as the method name instead of as the contract name. So this entry here will summarize all the methods of the uninteresting library contract as non-det. Okay. With these entries, not only can you not write a returns clause, because of course the different methods might return different types, you also don't even write the arguments because different methods take different argument types. So, so this underscore replaces the arguments and the return types and gets all methods of this contract. There's also only limited summary types that you can use here. Only what we call havocing summaries, so the non-det, havoc all, havoc ECF, and auto summaries can be used there. The other kind of summaries make certain assumptions about the return types of the methods, and since we don't know what those return types will all be different, the other summary types don't really make sense here. And as with these wildcards, you have to write a summary if you have a catch-all entry. You can't write env-free. Okay. Now, there's one more little detail that comes out of this, and this is also related to the expanded types that I'll talk about on the next slide. When you write a CVL function summary, so here balance summary would be a CVL function, you have to tell the prover how to encode the results of that summary. So, and that's what this expect clause is for. So now whenever you write a CVL function summary, you have to write expect, and this is the expected return type. And what this does is this tells the prover how to encode the output of this summary in a way that the contract can then consume. That information isn't in the bytecode for the contract because the contract's just going to get some call buffer or some return buffer, and it's going to unpack the return values from that. This tells the prover how to encode things into that buffer so that the contract code can extract it properly. So that's a new feature. It's a new restriction. This is useful both for these wildcard summaries and also because the types are more flexible, and sometimes this isn't clear from the return type of the summary. Okay. The third part of the CVL2 changes to the methods block I want to talk about are we now support more complex types. So in CVL1, if you had functions that took structs or returned structs, or if you wanted to work with enums or other user-defined types, the syntax for doing that was in some cases you just couldn't do it, and in other cases you had to use an ad hoc workaround like interpreting a struct as a tuple and breaking out its fields sort of manually. And it was complex and difficult to work with. CVL2 cleans this up considerably. In CVL2, you have access to almost all of the types in Solidity, and you can just write them the way you would in Solidity. There's two exceptions here. One is function types. So if you have a function that takes in a function or returns a function, that's something you can't put a methods block entry for. And so you'd have to use some kind of harnessing for that. And the other difference between Solidity types and methods block types are instead of writing the name of a contract or an interface, you have to just use address. Again, because that information all gets erased at the bytecode level, contract and interface types are just addresses. So But other than that, if you have a struct or you have an enum or any of the types in Solidity, you can also write those types directly in CVL2. So I have a couple examples for user-defined types. So one thing to note is when you refer to one of these user-defined types, like an enum or a struct, you have to refer to the contract where the type is defined. So in this example, I have a base contract with a status enum that has active and inactive. And if I want to, and then I have a token that extends that base contract, and it has a method that returns one of those status enums. So if I wanted to write an entry in my methods block for that, or if I wanted to use it in a CVL function, when I talk about the status return type here, I have to refer to which contract that status is defined in. And in this case, it's defined in the base contract, and so I have to write base.status here. So this is how an entry for this getStatus method would look. It's in the token contract, so I've written token.getStatus, but its return value, the type of its return is a base.status. And I can also use these enum and struct types in other places in CVL besides the methods block entry. So for example, my summary here can also declare that it returns a base.status. And if I want to access the individual elements of the enum, I have to also qualify those. So active here is base.status.active. Okay. So that's how you access user-defined types. You just have to know which contract they're defined in, and then you can access them from there. For reference types, that's another change in CVL2. In Solidity and in EVM, the arguments to methods, if they're complex arguments like structs or arrays, if they're reference types, so they get passed by reference, you need to indicate where that reference is. So is this a pointer into memory, or is it a pointer into storage or into the call data buffer? In Solidity, you have to write that down, and in CVL2, you also have to write that down. So now in your methods block, if you have a reference type like this user data struct, you have to indicate whether that method getBalance is expecting that to be a memory reference or a storage reference or a call data reference. This is only true, this restriction is only true in the methods block entries. In CVL, we interpret types in the methods block entries a little bit differently than types everywhere else, because there are types that are only available in CVL, types that are only available in EVM. And so when you're writing a CVL function, for example, you don't specify the location for a reference type, because in CVL, there are no reference types. Whereas in EVM, there are reference types, and when you do this summarization, we're interpreting this reference type as this CVL struct type here. So that's a little bit, maybe a little bit confusing, but the rule of thumb here is in the methods block, when you're referring to a Solidity method, that's where you have to include where that pointer resides. Okay. So that's reference types, structs and arrays, and user-defined types. And now with CVL2, you can write a summary for any method, regardless, again, with the exception of function pointers, regardless of what types of arguments it accepts or returns. Okay, so that's the first little section of the talk on the new methods block. I can pause here if there are any questions, or we can move on. Okay, let's move on. There's a lot of features to cover. So now I want to shift gears from sort of the syntax and just how you write down methods block entries to some of the new features that we've added. The next features I'm going to talk about are both in beta. They'll be available in the next release, or you can download the beta client if you want to use them now. And these are ways to get more information to function summaries so that you can write more general and more flexible summaries. So the first feature I want to talk about is really just removing a restriction that we had before. Previously, if you were using a CVL function to summarize a contract method, you weren't allowed to call contract methods from that summary. So here I've got this underline.transfer from contract method. I'm summarizing it with the transfer from summary, which is a CVL function defined here. And previously, you weren't able to do what I've done here, which is call a contract method from this summary function. This would have been an error until recently. And we've changed it so that it's no longer an error, and you're now allowed to call contract functions from your summaries. And this opens up a lot of flexibility. So in the example I've given here, we've used summarization to make a little wrapper around the transfer from method. So when the contract calls transfer from, it gets summarized by this summary, which then calls the original transfer from method, but also does some additional bookkeeping by updating this ghost. So there's a lot of things that you can kind of do with that pattern if you want to prove that a particular method gets called, or that it gets called a certain number of times, or that it gets called with certain arguments, things like that. This pattern is really useful for that. You can summarize the method to update some ghosts and then call the original method. You can also use this feature, for example, if you have a complex implementation of something and a simple implementation of something, you can summarize the complex implementation with the simple implementation. That's also a useful thing to be able to do. So this is a small change. It's only one line change in the documentation, right? Remove the restriction that you can't call contract functions. But this opens up a lot of new patterns that you can use in summarization. One caveat I'll mention, this isn't anything new having to do with this feature, but you can't call internal contract functions directly from CVL. So one thing that, and that includes this feature, so you also can't call contract functions from internal contract functions from summaries. And if you want to do that, you'll need to add a harness that is an external function that calls through to the internal function. Okay, so that's one new feature that is, as I said, available in beta. Another important feature, or really a pair of features, are this calledContract feature and this withENV feature. These both give you ways to pass more information to a CVL function summary. So in this example here, I've summarized the transfer method. Transfer, of course, takes in an address recipient and an amount that's being transferred. And I want to write a summary for this, and it's a wildcard entry, so I want to write a summary for all the transfer methods. Now, that would be a little bit hard previously, because if you think about how I want transfer to work, if I'm summarizing it, I might like to have a balance that I'm recording in a ghost or something like that. And so I'd like to, in the transfer summary, update that balance ghost. Of course, the problem is if I have multiple tokens, each one of them is going to have a separate balance for each address. And so, it's not clear how I would know which ghost to update because I don't have that information in the function summary, except now I do. So these two new features, calledContract and withENV, let me pass information about the call to the summary. So the first feature here, calledContract, this is the address of the receiver of the method. So if you call transfer on token T, then calledContract will be T. But if you call transfer on token S, calledContract will be S. And what that means is you can then pass that to your summarization method. In this case, pass it to transfer into this variable I've called token. And then I can use that to index into my mapping and update the balance for the appropriate token, right? So here I've got a ghost mapping that for each token, for each user, gives me their balance. And here I'm updating for the correct token, and it's whatever token transfer is called on, that's calledContract, that gets passed in as token. So that's the calledContract feature. And the other thing that is useful, if I'm calling transfer, and if somebody calls transfer, what should happen? Well, transfer moves tokens from the caller's account to the recipient's account. Well, who's the caller of transfer? Well, that's encoded in the message sender of the environment, right? And previously, there was no way to get that information in your summarization, but now there is. And that feature is the withENV clause. So when I write a summary for a contract function, I can add this withENV at the end, and that creates a new variable. In this case, I've called the variable E. That's what I usually do. And then I can pass that variable to my summary. So when transfer gets called, the message sender and the message value and the block timestamp and all of that stuff gets wrapped up in this environment E, gets passed to my summary, and then the summary can access the fields of that, just like it's exactly the same as the environment you would pass to a function when you're calling it from a rule. Okay, so in this case, my summary for transfer is going to look at the environment, find out who the sender was, and decrement their balance by amount. Okay, so these two features give you a lot more information that you can use inside the summary, and this lets you write much more flexible summaries. So for example, one of the things we're working on is a general ERC20 spec where you don't have to have a dispatcher with a separate contract implementation that you trust to sort of treat your underlying tokens, and you don't have to make multiple copies of that if you have multiple tokens. Instead, you can just write one methods block that summarizes all of the ERC20 methods and stores the state in ghosts, and you'll be able to write that once and use it for all the tokens that your protocol is interacting with. So these features give you a lot of power in writing summarizations and writing general summarizations, and these all will allow you to do a lot less setup, a lot less harnessing, and to write basically more fluent summarizations. Okay, so those are the new summarization features I wanted to talk about. Again, I'll pause. If there are any questions, I'm happy to take them, or we can move on. Okay, I know I'm covering a lot of stuff fast. I'll mention now, just in passing, we will post the video for this on our YouTube channel, and we'll also post the slides, and you can check out and ask questions on Discord, and I think we'll also put this talk in the documentation in the tutorial section as well. So you'll have access to this later and lots of opportunities to ask questions. Okay, so I'll continue. That was the summarization features. Next, I want to talk about two new features that give you access to the blockchain state. The first one's very simple. Previously, you weren't able to get the balance of the ether balance of a contract directly from spec. And it wasn't hard to work around. You could write a little harness method that just returned the balance of a given contract. If you've used the tool for any period of time, you've done that. But it's a little bit of a pain, and one of our goals here is we do want to reduce the effort of harnessing and so on. So there's now a way to access the ETH balance of a contract directly from CVL. The way that works is there's now a built-in ghost mapping called nativeBalances, and it's a mapping from addresses to ints, and gives you the balance of a given address. So for example, if I wanted to write a rule to check that depositing actually increases the balance of the vault, I could look at the native balance of the vault before, call deposit, and then look at the native balance of the vault after, and compare them as you would with a token balance or anything else. So this is just a syntax that gives you access to a piece of the blockchain state that you didn't have access to before. Pretty straightforward, but pretty useful, and removes some headaches. The other feature that lets you reason about the state of the blockchain is actually quite a big change and quite a useful feature. And this is the ability to compare storage variables. So storage variables, you may recall, are used to implement properties that compare different hypothetical executions. So a storage variable sort of wraps up all of the state of all of the contracts, all of their storage, and also all of the ghosts. And you can, in your rule, you can execute it at a particular storage, and that sort of resets the blockchain to that state before executing this function. And so let me walk through this rule a little bit. You may have written a rule like this. This is a very common hyper property is what we call them, a rule that compares hypothetical executions. So how does this rule work? Well, in this rule, we want to show that transfer does the same thing as transfer from, right? So how do we do that? Well, we have an amount and a sender and a recipient. We save the storage at the beginning before we call any blockchain methods, and I call this the initial state or the initial storage. We then call transfer, and this is just setting up an environment with the correct sender. And then here I'm storing the final storage. This is a little different than what you might have done in the past. In the past, you might have stored a balance after, right? So you'd store the balance before, the balance after, the first. But at any rate, then we call transfer from, but we do it at initial. And so this has the effect of rolling back everything in the world to the state that it was in before we called transfer, and then calling transfer from that initial state. And then we get a new storage after that. And again, previously, you probably would have gotten the balance after transfer from. So you would store the balance after transfer, store the balance after transfer from, and then you'd like to say the two balances are the same. The new feature here is the one that I've underlined, which is now you don't have to decide. What I really want to check is that the balances, the effect of transfer and transfer from on balances is the same, or the effect of transfer and transfer from on permissions is the same, or the effect of transfer and transfer from on any particular variable is the same. Instead, what I've written here is that the effect on the entire state of storage of all contracts and all the ghosts is the same. So this is really saying transfer and transfer from have exactly the same effect on everything. This is a really powerful feature. For example, you might have a method that you've written a simple but inefficient implementation for. And then you do a bunch of gas optimization, and you end up with a really complex method with maybe a lot of unchecked math, maybe some weird control flow. Who knows, right? Optimization leads to complicated programs. That's an error-prone process, so you'd like to check, hey, did I make any mistakes when I was doing that? Well, now you have a very easy way to write a rule that checks that your optimized version and your simplified version have the same effect on everything, right? You would just run both methods and then compare the storage after, and hopefully those two things would be the same. Okay. Comparing two storage variables like this compares all the storage, all the ETH balances of all contracts, all the ghost variables. And sometimes that's too much. Sometimes you might not care that you have exactly the same effect on one contract. You only care about maybe the effect on the underlying contract, or only the effect on the vault or whatever. And so there is a restricted form of comparison here, which is you can sort of narrow what you're comparing to just a particular contract. So for example, here, I could compare final one and then in brackets vault is equal to final two in brackets vault. And this checks that the storage of the vault contract in these two storage states are the same. And you can also narrow it down to just a single ghost variable or ghost function. So if I have a ghost X, I can also do final one of X equals final two of X. And that will compare these. You always have to be comparing the same thing on both sides of these equalities. I can't compare final one of vault to final two of underlying or something like that. That's disallowed. But this lets you restrict the scope of your comparison to a particular contract or ghost. By the way, this ghost variable could be the native balances variable that I talked about on the previous slide. And that will let you say that these methods have the same impact on the native ETH balances of the contracts. So those are two new powerful features for accessing the blockchain state and for writing rules that show that two functions are equivalent. Any questions on that before I move on? Okay, well, I'll move on. So the next thing I want to talk about are how integer types work in CVL2. And it's kind of different from how they work in CVL1, but it's a lot more streamlined and a lot more, there's a lot fewer ways to screw things up. So in CVL1 and in CVL2, we have different integer types. So we have uint types, just like in Solidity, and also sized uint types, uint 8 and uint 16 and uint 256 and all of those, as well as all of the int types of different sizes. And then there's also this CVL, I don't know why I put a star here. There's only one math int. There's a math int type in CVL. And a math int is an unbounded integer. It can hold an integer of any size negative infinity to positive infinity. Okay. In CVL1, you could assign math_ints into uint variables and uints into math_int variables. And there were complicated rules about when you could do that and when you couldn't. And there were cases where things could overflow. And there were easy ways to kind of make a mistake and end up, for example, hiding an overflow bug in your contract because you had an overflow bug in your spec. And that's not a great situation. So CVL2 makes pretty extensive changes to the way that you can do these implicit and explicit conversions. And it makes it much more sane. So overflow just can't happen in CVL anymore. And the way we guarantee that is anytime you do any arithmetic in CVL, it always produces a math_int. So you can never add together two uint8s and end up with something that's too big, because the result of adding two uint8s is a math_int, and there is no integer that's too big to be a math_int. Math_int can hold any integer. Okay, so because of this, there's nowhere in CVL any wraparound semantics, any overflow possible at all. Okay. In addition, you can implicitly convert, but only in places where it makes sense to do so, only when you're not going to lose information. So for example, you can always, if you have a uint, you can always store it in a math_int variable, because every uint is a math_int. And if you have a uint8, you can always store it in a uint16 variable or a uint64 or whatever, again, because you're never going to lose information by doing that. Okay, so these implicit conversions are possible, but only when it's safe. You can never store a math_int variable in a uint variable, because the math_int might be out of bounds for the uint. And so, what should happen in that case? If you have an implicit conversion there, who knows what will happen, right? So that's not allowed. And I have examples down here. In these examples, I've named my variables with their sizes. So x128 is a uint128. And so just as I said, it's fine to assign a uint128 into a uint256, no problem. I can store any integer into a math_int, no problem. But if I try and go the other way, if I try and store a uint128 into a uint64, there would be some narrowing here, and it's not clear what should happen if x128 is out of bounds, and so this will be disallowed by the type system. Similarly, if I try and assign a math_int to a uint, that'll be disallowed. And as I mentioned, mathematical operations always produce math_ints, so I can't add together two uint128s and store them in a uint128, because this might be bigger than max uint128, and what should happen in that case, it's unclear. So this is not allowed. And you might say, well, but I know if I add two 128-bit integers, it's going to be smaller than a 256-bit integer. And you're right, but we've still disallowed this. This is still going to produce a math_int. So here's something that could be sensible, but we decided not to implement. Okay, so that's all the implicit conversions. You're allowed to do them when you won't lose information, and not allowed to do them when you would lose information. But sometimes you do need to explicitly convert. Maybe I have a math_int and I want to pass it to a contract function that takes a uint, so I need to convert it. And the CVL2, we've tried to make very explicit what happens, and to give you control over what happens if the thing you're casting is out of range. So there are two casting operations for each of the uint and int sizes. There's a require cast and an assert cast. And they do what they say. So if I do require uint256 and I pass in a math_int, for example, this will require that math_int is in bounds for the uint256. If it's not, then that example will be discarded and nothing will get reported. And if it is, it'll be stored in the output of this. So here, for example, in this require uint64 of x128, if this x value is bigger than max uint64, then that counter example will just be discarded and nothing will happen, as if I had written a require statement. But if it's in bounds, then it'll be assigned into this uint64. The other kind of cast is an assert cast. And this works similarly, except instead of requiring that the value's in bounds, it asserts that the value's in bounds. So you'd use this if you think, I'm pretty sure that no matter what, this value is going to be in bounds. but I want to actually get a report if it's possible for it to not be in bounds. So for example, an assert cast would be a good example, would be a good choice down here. You remember I was saying if I add two 128-bit integers, I'm pretty sure that that should be able to fit in a 256-bit integer. I could use an assert cast there, and if I'm right in my logical reasoning, then that assert will never get triggered because it's impossible. But if it turns out that I was incorrect in my reasoning, then I'll get a nice report showing me, hey, in this case, you can add these two things together, and it won't and it'll overflow. Okay. So that's the require and the assert casts. They're very explicit about what happens if an integer is too large to fit in the type that you want to give it. There's one exception to this rule about implicit conversions, being able to do implicit conversions all over the place. And that's in comparisons. So if you're comparing two integers for equality or inequality or being not equal or whatever, these integer comparisons, these actually require you to have identical types, not just types that can be implicitly cast to each other, but actually identical types. And so we don't do implicit conversions directly on the left and right hand side of an equality, for example. And so there's one more cast operation, which is toMathInt, which you would think you wouldn't need because everything's a mathint, so you don't need to convert it to a mathint. But it's for this specific case where I'm doing comparison. In this example, I have a uint 256 and a uint 128. I can't just assert that they're equal because they have different types, and this rule says that you can't compare things with different types. And so what I can do instead is just cast them both to mathint, and then now both sides have the type mathint, and this comparison is okay. So toMathInt is specifically for this case where you're comparing two sides of an equality. Okay. And I've sort of told you a lot about how these things work, but I also want to spend a minute telling you how you should use them. And so here are some rules of thumb for how to use integer types the way that they're intended to be used. You can't get it wrong anymore. You can't accidentally have an overflow if you don't follow these rules. It's just that you might get some type errors, and then you'll have to think about, oh, do I change this type? Do I add a cast here? What do I do? So these rules of thumb will help you not have to add casts in places where they don't make sense. So what are the rules of thumb? You should use mathint wherever possible. It's an infinite precision number. It's easier for the prover to reason about. Most ghosts, for example, will be mathints. When a contract function outputs something, you probably want to store it in a mathint. Wherever you can, use a mathint. That's sort of the first rule here. Where can't you use a mathint? Well, you can't use a mathint if you're going to pass a value to a contract function, because contract functions can't take mathints as arguments. So that's the place where you would want to use the appropriate solidity type, a uint, uint 256 for the amount if you're going to pass that to the transfer from method. So that's a good place to use these solidity types. So if you're doing those things, getting outputs that are mathints, using inputs that are uints of the appropriate type, then you won't really need to use casts anywhere. The only place where you will need to use a cast is if you're doing some arithmetic or getting some value that's a mathint, and then you're wanting to pass that combined value back into a contract function. So in this case, if I want to add amount 1 and amount 2 together, I'm going to get a mathint. If I want to pass that to transfer from, then I'm going to have to convert it to a uint. And then at that point, you should think carefully, do I want to require or assert that the value is within bounds? And that's up, that depends on what property you're trying to prove. I'll just warn you that just like adding any require statement to your rule, adding a require cast can sort of hide certain counterexamples, because a require cast says ignore the cases where this is out of bounds. And so that's more dangerous than an assert cast. So I would default to an assert cast, even if you think something can't possibly be out of bounds. You should use an assert cast to double check your intuition there. And then I would only use the require cast if I use the assert cast and it gives me a counterexample, and I'm like, I don't actually care about that counterexample. In this case, I care about what happens when I transfer from with the sum of these two values. Well, it doesn't even make sense, to consider the case where the sum of these two values is out of bounds. And so that's why I've used a required cast here. So when you get to the point where you need to use a cast, then you should really think about what do I want to happen if the value I'm casting is out of bounds. So that's how integer types work in CVL2. Any questions there? All right, let me move on to the last feature. I know this has been a wild whirlwind tour, and there's a lot of stuff that I'm covering, but we're to the last feature here. So the last feature is for producing examples of good behavior. So if you think about a rule, right, in CVL, you're saying here's what should happen, and you're asking the prover to tell you if there's any ways that the thing you think should happen doesn't happen, right? So you get violations of the properties that you expect to hold. But sometimes it's useful to have an example to help you reason about what's going on in the contract, or to convince yourself that that it's possible for something not to revert, for example, or to convince yourself that the require statements you've written don't rule out interesting cases, or just to give a demonstrative example because you're trying to show somebody what happens when they call a certain method. So an assert statement isn't going to help you with that, and that's what the satisfy statement is for. So instead of giving you an example of where something goes wrong, a satisfy statement gives you an example of where something goes right. So you can write a rule, and instead of putting assert, you just write satisfy. And then the prover will try to give you an example where this satisfy statement evaluates to true. Okay. And as I said, this lets you create examples or check that it's possible for a function to not revert. So just as a simple example here, I might want to give an example where the user can withdraw everything from their account. And so I'm going to call the withdraw method here, and then I'm going to ask the prover to satisfy the fact that the balance of the user is 0 after withdrawing. Okay, so the idea here is I have a user, they call withdraw, I want it to be possible for them to call withdraw in a way that empties their account. Okay, and if I were to run this rule, the prover would give me an example where the balance of the user after calling withdraw is 0, which is what I would be looking for. Now, you have to use care when you're using the satisfy statement, because the prover is going to be a little bit devious. It's not going to prove that it's possible in any starting state to drain your account. It's just going to prove that there is some starting state where you can call withdraw with some amount in some environment and end up with the user having a balance of 0. And so often it'll prove examples that you think are produce examples that you think are kind of dumb. So for example, if I were to run this rule, the prover might just choose a scenario where the user's balance was initially 0 and they withdraw 0 tokens. And then of course their balance afterward is 0. So this doesn't prove to me that my withdraw method is working correctly. It just gives me one example of the withdraw method doing one thing that I want it to. So this, you shouldn't use satisfy to convince yourself that something is correct. That's what assertions are for. That's what properties are for. Satisfy is only a way to give you demonstrative examples and to help you walk through your code and understand what it's doing. What you can do with a satisfy statement, if I ran this and I got an example and it said, oh, okay, well, the starting balance is 0, then of course the ending balance is going to be 0. I might say, okay, well, that's not an interesting case. And so I could add a require statement here that says, well, let's require the starting balance is positive. And then I could run this, and then I'd get a case where I'm able to withdraw everything. But again, that still doesn't guarantee that the function's correct, because maybe withdraw has some round off errors that can happen, but they only happen on certain, multiples, or if you're not on a certain multiple of, some exchange rate or whatever, you might get an example that is on that multiple of the exchange rate. But that doesn't mean there's not a bug if your balance is something other than one of those multiples to start. So again, I just need to emphasize, satisfy isn't going to prove to you that things are working correctly. It's going to give you one example to help you understand what's going on, or to prove that you have functions that don't revert no matter what. Okay. All right, so that was the last feature I wanted to talk about. We've gone through a lot of things. In this last slide, I just want to go over sort of what we talked about and point you to the appropriate parts of the documentation. So we talked about, sorry, is there a question?
Yeah, there is a question in the chat, still about the conversions.
Okay, well, let me go through this and then I'll take questions right after that.
Okay.
Okay, so just want to summarize what we talked about. We talked about the new changes to the methods block. You need internal and external, you need function and semicolon. You need to include location specifiers for reference types. There are a bunch of changes with CVL2. These are all described in detail in the CVL2 changes document. I would encourage you to read through that. It really goes through all of the things that changed in CVL2 in some detail. The integer type changes are also in there that I just talked about. A lot of the information in the methods block is both actually in the CVL2 changes, but some of the things like catch-all summaries and some of the new summarization features that have happened since CVL2 are just in the methods block reference manual. The native balances and storage comparison, those are also features that are new since CVL2. You can find those in the documentation on expressions in CVL. And the satisfy statements that we just talked about, there's actually a section in the user guide kind of walking you through how to, how to look at an example and make sure it's the right one. So that's where I'd point you for that. So that's a bunch of features, a lot of new stuff. We hope that this will help you write more of the specs that you want to write and inspire you to think of new kinds of properties and new kinds of setups you can do for your own protocols. So thank you, and now I'll take questions. And it sounds like there was a question, Narit, that you were asking.
Yes, so everyone can unmute now if you have a question. So there's a question from Quentin. Would it be possible to automatically convert both sides of a comparison to method? What would be the downside of doing that?
So it's a good question, and it's something we're thinking about. We have some examples where doing that could actually, for example, hide an overflow. In some cases, especially before we added ghost variable updates to CVL, you would basically use a require statement to update a ghost. And if you're doing that, then that require statement is acting kind of like a require cast, which isn't what you want. And so the reason we added to mathint instead of having this implicit casting for comparisons was to handle cases like that. We're kind of thinking about what's the right generalization of that, and if there are more places we can do automated conversions. But we wanted to sort of better safe than sorry until we really nail down all the implications of that.
Okay, thanks a lot, and thanks for the presentation.
I had a question about the satisfy.
Yes.
You're saying it does not consider all possible starting paths, but if the satisfy is violated, meaning like the thing could not, the tool couldn't find the path, it means that it did consider everything and couldn't reach it, right?
That's right. Yes.
All right. Yeah. I have also a few other questions, but maybe you can also take it offline. But if no one else asks, then I ask about the summarization. You said like that when I summarize a function, I can call the same function again. So how does the tool do that? Like if I have a summarization of F and I want to call G,
yes.
The summarization of G would not be called, like,
right.
How does that work?
Good question. First of all calls directly from spec are not no calls directly from spec are summarized. And that includes calls from summarizations. So if you summarize F, and then in this summary you call G, and if you would summarize G as well, you wouldn't call the summary for G, you'd call the original G.
Awesome.
So
thank you.
That works. Same rule here is that calls from spec aren't summarized.
Yeah, it makes sense. I just wanted to know.
Yeah,
that,
the other thing
I can't make a loop somehow.
Yeah, you can make a loop. Actually, that was the second thing I was going to say, because if I summarize F and F calls, and the summary for F calls G, and then G calls F, and then I come back to the summary for F, I now have a recursive call, and that is possible. And we handle it actually exactly the same way we would if there was recursion in the contracts, which is actually the same way we unroll loops. There's a recursion limit built into the prover, and you can set it with a command line flag. And there's you can set it so that you either will get an assertion violation or that you'll ignore counterexamples if you go past that recursion limit. So
awesome. Another question about summarization was like, what statements are allowed inside summarizations? Like beside ghost manipulations and now solidity calls. I know that in CVL1 it was a bit limited. So like, can I add parameters or can I add requires or asserts?
I think so. I as far as I know, there are now no special limitations for functions that are used as summaries.
Awesome.
Yeah, I'm pretty sure that's the case. Other questions?
Another question is about the types in the methods blocks. So is there a return type of when I need to define the return types? Are they a solidity type or are they CVL types? Like I guess no function could return a math int or get a math int, but
right.
You also mentioned something about like specifying if it's in memory or not. So I was just worrying about it.
Good question. Return types in the methods block and argument types are both what we call EVM types or solidity types. So if I did have a reference type as a return value, I would need to indicate whether it's a memory or a call data or a storage pointer that's being returned. But then when I pass that to the summary now, this is a CVL type, and so it would not in the summary indicate that. So the conversion from EVM to CVL sort of happens where that arrow is. That's when the the solidity types here get converted to the CVL types.
Awesome. And really last question, now that we have this any contract summary, I was wondering, can I make like the default summary for allowance to be non-det, but for a specific contract to be a dispatcher?
Yes, absolutely. So the question was, can I have both a wildcard sort of setting the general case and then override it for a specific contract? And the answer is yes. And it works how you would expect, which is the more specific one applies for any given method call. So I think, and in fact, I think you can even mix those with these all methods. So you can have an all method and then a wildcard and then a specific entry. And I don't, off the top of my head between these two, I don't remember how the details of how it resolves, but you can definitely override either of these with a entry for a specific method of a specific contract.
That's awesome. Thanks.